Welcome to Introduction to Computer Science and Scratch Programming. This is Chapter 1, Part 1, Introduction to Computers and Computer Hardware. I'm Brett Owens. I'll be your guide. Our objectives for this lesson are to know the definition of computer science, hardware, and computer, to understand the timeline for the development of computers from the origin of the word computer in the 1400s to the development of modern-day computers around 1822, ending in 1943. This course provides a basic introduction to computers and programming using the Scratch programming language. This presentation follows the text that was developed for the online course provided at brettp.com. What is computer science? Computer science is the scientific study of the theories, methods, and procedures of processing information using computers. It includes the study of both hardware, the computer and devices that are attached to it, and software, the programs and applications that are used to process information. The term computer first appeared in the early 1400s and referred to a person who could quickly and easily perform mathematical calculations. Fra Luca Bartolomeo de Porcioli, 1445 to 1517, was an Italian mathematician, Franciscan friar, collaborator with Leonardo da Vinci, and seminal contributor to the field now known as accounting, and is also referred to as the father of bookkeeping. Porcioli is one of the first men to be referred to using the term computer. The figure to your left shows Jacopo de' Barbari's painting of Porcioli. In this painting, Porcioli is depicted performing mathematical calculations while a noble observes. It's arguable that the first device to use concepts of modern-day computational devices was developed in 1822 by Charles Babbage. That device was a mechanical device known as the difference engine and was able to compute several sets of numbers and produce a hard copy of the results.
result column is even. This is the result column, and the numbers are stacked up this way with the least significant digit starting here. So this would be the units position, then the tens, then the hundreds and thousands, and so on going up. We started the knurled nut and go up. The bottom 5 are doing another equation at the same time. We're doing a fifth order polynomial up here at the top, and it turns out to be this polynomial. 9x to the fifth plus 5x to the fourth plus x cubed plus 7x squared plus 4x plus 41. Now, would you like to do that one by hand, by yourself, by hand? I don't think so. But you could at least do the first 7 by hand and get a table. And then using the table, you can compute it on and on and on forever. Okay? So, what we put into the machine are the numbers from the difference table for this in the top ranks, above from the knurled nut on up. On the bottom, we have a very simple equation called result equals x. So when x equals 0, the result is 0. When x equals 1, the result is 1. When x equals 2, the result is 2. Okay, for consecutive values of x. And what's the difference? Well, 0 from 1 is 1. 1 from 2 is 1. 2 from 3 is 1. And so on. The difference is 1, a constant. And there's nothing, everything else to the right is 0. So we have a 1 in this column that keeps adding to this and getting reset, and adding to this and getting reset. Okay? So we just keep, what x is down here? We keep track of x. So we know for x what the result is. It's matched. Now how does it work? Well, the odd column counts down to 0. It's a destructive read. So if we look at the first column that has a number in it, this is the number column right here. It has 1,080.
Let's give them a 2 result t-shirt.
All right, sure.
Okay. I'd love to try.
So watch this a little bit. That's the add, this is the reset. That's the add, and that's the reset of the evens. So there's the odd reset, the even, and the even reset. Now what do I mean by that? Well, when the odd column counts down to 0, this gear in between transmits the value that's being turned as it counts down through the gear in the middle to the other column next to it. And so that column counts up. Now you might say to yourself, well, how's that possible? Well, the odd column has the numbers on the number wheels that go around in a counterclockwise direction. In order to count them down, you turn the gear counterclockwise. And when you do that, something like the 8 gear will go 8, 7, 6, 5, 4, 3, 2, 1, 0. And as it turns counterclockwise, the gear in between will turn out 8 positions in a clockwise direction. It's engaged to the even gear, which turns counterclockwise and turns 8 positions. But when the even turns 8 positions, its numbers are on here in a clockwise. Turning them counterclockwise causes it to go 1, 2, 3, 4, 5, 6, 7, 8. It counts up. So the odd counts down, the even counts up, because the numbers are on the wheels in the opposite directions. Now this even is hooked up to another odd. That's a clockwise turning number hooked up to a counterclockwise turning number. And now we simply count down the evens, okay, and count up the odds. So the process repeats itself, okay, for the opposite direction. Now you might say to yourself, okay, well, I'm all done counting down and I've added it to the even column. How do I get the value back to being what it was? And the answer is this gear lifts up so that one side is engaged with the counting down side, the odds, and disengages from the even. And then the gear in between gets set back to its 0 point. So if it counted out 8 positions, it goes back 8 positions, and it turns the gear back in a clockwise direction, it counts it back up. So it originally counts down, and then it gets counted back up. It gets reset. Okay? Now how's it able to do that? Well, it turns out these gears are set up so that they're double thick on one side and single thick on the other. So when they're down touching at the bottom, they're hooked up between the two. But when they go up a little bit, the even side is no longer touching the even gear, but it's still touching the odd gear, and the odd gear will simply get reset. And then it moves up again. And when it moves up again, it's not touching either side. It disengages completely. Because during that part of the cycle, we're doing the same thing between the even and the odd next door. The its gear drops down, adds from one gear to the next, moves up a level, and resets the even. And then moves up again, so it's disengaged, so we can go back to doing the odds again. So a complete cycle is odd is added to even, odd is reset, disengage. The other side does even is added to odd, even is reset, disengage, and back and forth we go. And you can watch that with these two levers. These two levers will go three positions, and just as they get to the top on one side, the other side drops down. It's like walking feet. Okay? Now let's do some more turning. Right here. And you'll see it now. Watch those levers down there. Okay.
That's 3 more answers. We've done 5 answers while you were here.
It takes about 8 seconds to compute one new value. Now, the question that, of course, immediately arises in your head is, why? Why are we doing this? What's it for? Well, the answer turns out to be on this piece of paper, on this sheet of paper. Logarithm tables, sine tables, cosine tables, you name it. And we have to go back now to the history of what brought us to the realization that this machine was required at some point in time.
Considered to be one of the first electronically programmable computers, the ENIAC, Electronic Numerical Integrator and Computer, was invented in 1943 by Presper Eckert and John Mulchley at the University of Pennsylvania. This device weighed almost 100,000 pounds, took up just under 2,000 square feet, and had around 18,000 vacuum tubes.
In February 1946, the U.S. government revealed to the public the existence of a secret computer, which had been developed under the code name Project PX. The computer was called ENIAC, a massive electronic digital computer. Begun in 1943, under the authority of the U.S. Army, the ENIAC was developed at the Moore School of Electrical Engineering at the University of Pennsylvania. The following film is perhaps one of the earliest existing video records of a fully operational electronic digital computer ever made. This originally silent film has been carefully edited to remove lighting imperfections and other issues present in the original. In all other respects, it contains 100% of the original film footage and is provided here for historical purposes. ENIAC stands for Electronic Numerical Integrator and Computer. It was the world's first large-scale digital electronic general-purpose computer. It was designed to be capable of being reprogrammed to solve a large number of numerical problems. ENIAC was conceived and designed by John Mulchley and J. Presper Eckert of the University of Pennsylvania. They headed up a team of engineers and others that worked on the ENIAC project, which began in 1943. The team that worked on the ENIAC included a large number of women who were instrumental in the detailed task of manually programming this giant machine. Programming was accomplished by setting switches and connecting wires according to specific instructions, which were first worked out on paper and then carefully carried out and tested. Mapping the program out on paper took weeks. The task of setting the switches and wiring cables to match the program diagram then took many days to complete. When it was originally designed, there was no written manual on how to program the ENIAC. The women involved in the actual programming of the machine relied on block diagrams and logic diagrams of the machine's operation, as well as personal talks with the engineers directly responsible for specific parts of the ENIAC machine. In 1997, the 6 women who did most of the programming of ENIAC were inducted into the Women in Technology International Hall of Fame. In addition to switch panels and wiring panels, ENIAC used an IBM punch card reader for input and an IBM card punch machine for data output. The timing of these machines was synchronized with the operation of the ENIAC itself. The ENIAC was a very large machine. It weighed over 30 tons. The ENIAC had a total of 40 panels and utilized 18,000 vacuum tubes, with 70,000 resistors and 10,000 capacitors. ENIAC also had its own dedicated power lines. To keep the vacuum tubes from overheating, the room was air-cooled. When ENIAC was announced in 1946, the news media called it a giant brain. Its computing speed was 1,000 times greater than that of electromechanical machines. This computational power, along with its general-purpose programmability, made it a technical marvel of its time. ENIAC's design and construction was financed by the United States Army. The construction contract was signed on June 5, 1943, and work on the computer began the following month. The cost of the ENIAC in 1946 was just under $500,000, which is equivalent to over $6 million today. ENIAC was formally accepted by the U.S. Army in July 1946. ENIAC was temporarily shut down on November 9, 1946, for a refurbishment and a memory upgrade. It was then transferred to Aberdeen Proving Ground, Maryland, in 1947. There, on July 29, 1947, it was turned on and remained in continuous operation until it was powered down on October 2, 1955. ENIAC was initially designed to calculate artillery firing tables for the United States Army's Ballistic Research Laboratory. A typical ballistics calculation that previously might have taken 12 hours using a desktop mechanical calculator could now be done in just 30 seconds. The ENIAC's other applications included weather prediction, atomic energy calculations, cosmic ray studies, thermal ignition, random number studies, wind tunnel design, and other scientific uses. Here, output from one of ENIAC's printers is being produced. In this scene, we see brilliant ENIAC designers J. Presper Eckert on the left and John Mauchly on the right. They would continue their involvement in computer design and manufacture far beyond ENIAC in the years to come. Even before ENIAC was fully operational, both Eckert and Mauchly realized they could design and build a significantly more capable and efficient computer, incorporating some design improvements. They began working on a computer they called the EDVAC. EDVAC was delivered to the U.S. Army's Ballistics Research Laboratory in 1949 and made fully operational by 1951. In 1946, the University of Pennsylvania adopted a new patent policy, which would have required Eckert and Mauchly to assign all their patents to the university if they stayed beyond March. Unable to reach agreement with the university, both Eckert and Mauchly left the Moore School in March 1946, along with many of the senior engineering staff. Soon afterwards, Eckert and Mauchly started up the Electronic Control Company. They later changed the name to the Eckert-Mauchly Computer Corporation, or EMCC. By October 9, 1947, they had a contract with Northrop Aircraft to build the BINAC, or Binary Automatic Computer. EMCC was officially incorporated in December 1947 and was the first commercial computer company founded specifically to produce electronic digital computers. The EMCC had also been working on another computer, the UNIVAC. Before the UNIVAC was completed, Remington Rand purchased EMCC, which then became the UNIVAC division of Remington Rand. UNIVAC 1 was released in 1951. In 1955, Sperry merged with Remington Rand, and the name Sperry UNIVAC was used on many computers until Sperry dropped the name UNIVAC in 1984. Sperry merged with Burroughs in 1986, and that company became Unisys. Here, Herman Goldstein, one of the development team, reads ballistics data output. Today, a portion of the ENIAC still resides at the University of Pennsylvania. Other components of ENIAC reside at the Smithsonian Institution in Washington, D.C., the Computer History Museum in Mountain View, California, and other locations. ENIAC remains a milestone in computer development. The brilliant work of Eckert, Mauchly, and the many men and women who contributed to this amazing industry is a legacy that lives on to this day.
Later, the Manchester Mark I and Harvard Mark I computers were developed and used the same method of programming. That is, the programming was an integral part of the computer, and these devices used electronic relays to represent zeros or ones. Part of the Harvard Mark I is shown to the right. A relay was either on or off, and groups of relays were assigned values that could be converted into common characters or used to perform mathematical calculations in base 2 math rather than the traditional base 10 mathematics system that we commonly use today. The Manchester Mark I is shown to the right. This concludes Chapter 1, Part 1. We'll pick up with Chapter 1, Part 2 tomorrow, where we'll be discovering the source or the information and the origin of the term computer bug as we study more about the Manchester and Harvard Mark I's.